This is the See I Can for Year 10 Linear Graphs and Equations, page 2. State the coordinate of the intersection of two lines. So just in case we can't see it on the black and white copy here, we've got two lines here on a number plane. And all we want to know is what is the coordinates of the point of intersection where they cross. Now that's that point in there. We want x, y. That's 0 on the x, 3 on the y-axis. That's all we're asking for. We're not asking just for the y-intercept of 3 because they said the point of intersection, 0, 3 in brackets. Now, just in case we can't see these lines here, I'll highlight them in red. Two lines, and I want to know the coordinates of that point of intersection. So we go down here to the x, which is 4, and across to the y, which is 3. That's all we need. Write an equation of a line that is parallel or perpendicular to another. Now, lines that are parallel have the same gradient. So, the gradient of this line is in front of the x. This is just asking for any equation of any line that has that same gradient. Y equals 2/3 x, and because you can make up any line, you can make up any y-intercept. Let's do -2, but it could have been anything. This is a bit tricky. This is a bit more than a C grade. When lines are perpendicular, their gradients are swapped positive to negative, and the fraction of the gradient is flipped. So what that means is, if the gradient of this one was positive, for a gradient to be perpendicular, we'd have to make it negative, and we'd have to flip the fraction upside down. So a perpendicular line to this one is y equals -3/2x, and because they could give us any line at all, we can choose any y-intercept. Let's use +1. So perpendicular lines, that's getting a little bit tricky, more of a B grade. Graphing equations of straight lines to solve simultaneous equations graphically. When I find the point where two lines cross, it's called solving a simultaneous equation because that's when they're simultaneously in the same spot with the same x and y values. We can be asked to solve them. They can solve lots of problems like this one. If you're asked to solve them by graphing, you graph both the lines and you find the point where they cross. So here they'd graphed them for you. Here we have to graph them and then find the point where they cross. Remember, when you're graphing a line, each line needs a table of values. They haven't given me the x values. The easiest way to do it is to have 0, 1, 2, 3. But I'm going to put -1 in, just in case the test has some negative ones. But if they don't fill this in, you can choose it. Just go from 0, 1, 2, 3. That's fine. We just need to graph the line. And this is our table of values with the imaginary what if x column. So remember, always use the calculator for any negatives. The rule is 2 times x plus 4. So when x is -1, that's 2 times -1, and then the rest of the rule is plus 4. 2. You can just always use the calculator if you want. When x is 0, 2 times 0 plus 4. 4. When x is 1, 2 times 1 plus 4. 6. And now we'll start to see the pattern. 2, 4, 6, 8. This line also needs its table of values, but it's a good idea to graph this line first so we don't get mixed up. Graph each pair of points on the number plane. X is -1, y is 2. 0, 4, 1, 6, 2, 8. Check that your points make a straight line. They do. Very carefully, because we're going to have to work out where these lines cross, so we've got to be very accurate. Rule a line all the way through the number plane. Arrows at either end, label it with its rule, because you're going to be putting two lines on this and you want to know which is which. Let's graph this one. So here the rule is -3x plus 9. That's -3 times -1 plus 9. Got 12. When x is 0, -3 times 0 plus 9, x is 9. When x is 1, -3 times 1 plus 9. X is 6, and now we see the pattern, 12, 9, 6, 3. But if you can't see the pattern, we can always use the calculator again. Plot these points. -1, 12. Oh, it doesn't fit on the graph, so we can leave it off. 0, 9. 1, 6. Oh, we've found the point of intersection. 2, 3. Ruler through your points carefully, arrows at either end, label your line with the rule, and that's where they intersect. And you can see it's actually there on the table of values. The point of intersection is 1, 6. It's the point where it's the same on both tables of values, where they cross over on the graph. So that's how you solve simultaneous equations, by graphing. And here's a problem that needs us to use simultaneous equations. There's the cost of hiring two different removalist companies. Let's colour these in so that we can see it. There's A Removals in red and B Removals, or Best Removals, in green. Determine, well, that means find out, the number of kilometres for which the total cost of the removalists is the same. So this is the distance we're moving, and this is the cost, and the cost is the same when the graphs cross over. Now, it's a little bit hard on graphs sometimes to see exactly, so we do our best. We look for where it's most likely to have that crossover. Go down to here, that's 200 kilometres. What's the price when the total cost is equal? So when the cost is equal, the price is, oh, it comes out to there, so we've got to work out, that's 1,000, that's 1,500, that's 1, 2, 3, 4, 5 little gaps, so each of those must be 100, so that's 1,400. If a person wanted to move 400 kilometres, which company would be cheaper and by how much? So we've got to go to 400 kilometres and move up the graph to see which one has a lower cost. So A Removals is cheaper, and we need to work out how much the difference is. That looks like $200 to me. If we wanted to be very, very accurate, we could say by approximately $200, because we are reading from a graph. And the same here, approximately and approximately, because we're just reading from the graph and we don't have an equation, so that we can't calculate it exactly.